Take a look at any aircraft from the first decade of aviation, about 1903 to 1915. The Wright Flyer, the Blériot 11, the Nieuport 10, every single one was made mostly out of wood and canvas. Jump ahead just 20 years later, and you can hardly find any aircraft from the period not made out of metal. But what changed? Simply in 1915, the first all-metal aircraft, the Junkers J-1, flew its maiden flight. Designed by legendary aviation pioneer Hugo Junkers, this aircraft revolutionized aircraft design, and the days of wooden aircraft were numbered. Initially, designers stuck to wood as the main structural component out of necessity. Wood has a relatively high strength-to-weight ratio, a measure of its force per unit area versus its density. Oak wood, for example, has a strength-to-weight ratio of about 115 kilonewton meters per kilogram, about the same as modern 6061 aluminum alloy. Additionally, it was easily available and easy to work with. No advanced machining was needed to make specific parts, and a skilled carpenter could create anything easily. From a performance standpoint, it was advantageous as well. Early engines were unable to carry large loads, and any additional weight would make an aircraft unable to fly or reach maximum performance. As with so many other technologies, this began to change with the advent of the First World War. Guns, bombs, and larger and more powerful engines needed to be carried, and wood and canvas are less than bulletproof. Additionally, wood has other flaws that prevent its use as an industrial material. Its performance can be altered and structure damaged by rain, and its quality is not consistent. For example, one tree may be particularly strong, while another exceptionally weak, a serious problem when trying to design aircraft that perform the same across large production runs. Wood is also anisotropic, meaning that it will have different characteristics when oriented in different ways. This is a result of the natural grain pattern of the wood. Given the realities and requirements of large-scale aircraft manufacturing, many began to look towards metal as the aircraft manufacturing material of choice. The first to practically do so was Hugo Junkers and the Junkers J-1 in 1915. Using a combination of sheet metal, corrugated steel, and recently invented aluminum alloy Duralumin, Junkers created a sturdy aircraft prototype that demonstrated the feasibility of all-metal aircraft capable of much higher speeds and greater durability than the planes currently in service. The lessons learned from this prototype led to the first mass-produced all-metal airplane, the Junkers J-4, just 2 years later in 1917. Its metal structure made it easy to manufacture by low-skilled workers and provided protection to ensure that none were shut down in its first year of combat experience. From this point onwards, metal slowly began to take over the skies. Increasing engine power and skill in metal fabrication made wood's early advantages obsolete. This development continued into the 1920s. NACA, the predecessor to NASA, reiterated the above reasoning in 1920, concluding, quote, "It is felt that in the future all large airplanes must necessarily be constructed of metal." The Stout II-AT was the first such metal aircraft produced by the United States, with the first flight in 1924. Even with these developments, however, it took time to resolve many of the issues inherent with metal. While strong, metal buckles much more easily than wood. To combat this, designers had to incorporate more complicated shapes and internal structures. As a result, a metal aircraft of similar weight to a wooden one cost much more. Metal development also progressed slowly. While more durable than wood, duralumin corroded easily and could be brittle, posing its own set of challenges. It was only with the invention of Alclad in 1927 by Alcoa that aluminum would become totally superior to wood. By the 1930s, wood was barely used anymore. Metal had overcome most of the shortcomings that held it back. Increased metal content also allowed for secondary advantages of simplified aircraft construction. Wings made of wood had to be braced by external wires and struts connected to other parts of the aircraft in order to keep them in place. This limited design possibilities, greatly increased drag, and made maintenance much more complicated. Metal wings were free from this, however, and allowed for cantilevered wings to be used for flight. Inside a metal wing, a network of stringers, ribs, and spars allow the loads experienced by the skin of the wing in flight to be distributed inside. The strength of the metal used allows for this to happen without the wing snapping off, as was the worry with unbraced wooden wings. Overall, the switch to metal allowed aircraft to reach increased speeds, greater heights, and longer distances, and just as new and better materials allowed the switch to metal in the first place, Continued material development provides new opportunities for aircraft development.